So today, the goal is to do a little calculus on what's called Newton's synthesis. This is a really important outcome, and it's a little bit complicated, but not hard. It's just tricky, I think is the right word for it. So universal gravitation, that's Newton's equation. The force of gravity is equal to G mass 1 mass 2 over separation squared that we learned in the other class. Well, as you certainly would expect, this being the calculus-based section, we're not going to take it just like that. Because things are,
Dang.
Things are not made up of a piece of mass here and a piece of mass here. The mass is distributed continuously. And so if we have a continuous distribution, we can't just add up the mass from each individual point. We have to take an integral over the continuous distribution. And so this is going to become df vector minus gm1 dm over r squared. Now, I need to put in a direction to it, and so I put r hat. The minus and r hat are additions that we could have put in the non-calculus version. Those are telling us the direction. The gravitational force is always attractive, and the r hat direction is pointing away from whatever your object is. So since it's attractive, it should be pointing toward the object. That's why it's at the minus sign. The r hat is telling us the direction. R hat means a vector of length 1 in the direction of the r vector. And so, in fact, on the next slide, I'll have this written again with two forms of it. The second form is using the definition that r hat is equal to the r vector divided by r magnitude. Right? R vector divided by r magnitude means it's going to have a length of 1, but the direction of r vector. So here is it written out in neat, you can read typewriting.
What do you mean R cubed?
Right, because we replaced r hat with r vector over r squared times r became r cubed on the bottom. So that was simply the change, like I just said. I'll write it again. Using r hat as r vector over r, that meant I had to replace the r hat on top with r vector and the r squared on bottom with r cubed when I put this in. So that's what we're going to use. And now we have the problem statement. Consider a spherical shell of uniform mass. That is, the mass distribution is uniform over the entire surface of that shell. What we want to find is, what is the force of gravity going to be on something that's inside of that shell and something that's outside of the shell? So we're going to do the problem twice, once for inside and once for outside. So we start with a picture. Now, the three of you who are in calculus, you've been going through similar things, but not the same thing. We need to integrate over the surface. You've been doing integrals over the surface, right? It was on your last test. Well, we are not going to integrate on the circle. We are going to just simply say, that is, we're not going to do a rotation about it. We're simply going to say that if you rotate about, you can make this little strip that has a length. The red part that I've drawn will be the radius of the circle times d theta. R d theta is the length of that stripe I've drawn. And then if it goes around a complete circle, a circle of rotation, then you will have the length of that circle is 2 pi times whatever the radius of that circle is. So I can find that circle's radius that there would be the radius for the circle of it being spun. And so just using trigonometry, if this angle theta is defined as shown, then I can break my triangle up into a right triangle here and have the hypotenuse of that right triangle is capital R, the radius of the circle, and I'm looking for the opposite side. So what's the trig function that relates opposite side with hypotenuse? Sine. And so that means I'm going to have the radius of this circle here is capital R times sine of theta. So if I go around the circle of that radius, the length of that is, that's weird. Therefore, those three dots mean therefore. The length for that strip is equal to 2 pi times r sine theta. I think it's my finger down below that's making it goof up there. So the total area of spinning this thing would be 2 pi times r sine theta, the length, times the width, which was r d theta. And so I'm going to call that my d area. So I'm going to have d area is equal to the width times the length. Come on. And of course, you put that together, that's equal to r squared 2 pi sine theta d theta. Oops. So that's the area that you're going to have for that circle that's in lilac color there. And then you're going to have to take that area and, well, we haven't actually gotten to, I haven't explained where I'm going. I should. I need dm. I need the piece of mass that is on that strip. And so I found the area of the strip, and I have it here. My dm, the piece of mass, will be a density times d area. This is no sigma instead of rho. Sigma is the mass per unit area. We use a different symbol for it. And since I'm working on a shell of small thickness, I am simply going to say that sigma is the total mass of the shell divided by the total area of the shell. One thing you guys, I'm guessing, don't know, the area of the sphere is 4 pi r squared. And so that's why A is replaced with 4 pi r squared, because that is the equation for the area of the sphere, the surface area of the sphere. And so sigma is going to be mass over 4 pi r squared. So if I put that all together, here's the dA that we just did on the previous page. And so dm is sigma times dA. So there's the sigma and then the dA. Or this big thing here, m over 4 pi r squared is sigma times 2 pi r squared sine theta d theta. But notice, 4 and 2 gives me 1/2. Pi's cancel, r squareds cancel. And it's just m over 2 sine theta d theta. So it got easy. Started looking complicated. Got easy so far. So what have I done? I found dm is m over 2, where this m here is the mass of my shell. Sine theta d theta. Now that we have that, we're going to try to find the force in just one direction. Notice I use the x direction here. Symmetry tells me that the net force in the direction that would be vertical here would have to be 0. Because I have exactly the same amount of mass above as I have below with the same geometry. And furthermore, if I were to come this direction or that direction, the forces in that direction also have to be 0 for the same symmetry argument. So the only force that doesn't have to be 0 is going to be the force in the horizontal direction. So that's the only one we're going to find. Yeah.
So in the last couple of slides, it's been negative g. Like the questions have a negative in it. Why
Yes.
doesn't it have one?
Okay, so why is there no negative here?
Is it because it's horizontal and it's not?
So we have to go back to here to see the negative sign you're talking about, right?
Yeah.
So it's in the direction the minus and r hat are to tell us the direction of the force. So if we look at, our picture here, I'm going to have the force due to anything that's to the left of my M is going to be going in that direction. The force due to anything to the right is going to be that direction. Agree?
Yeah.
Okay, so we drop off the minus sign and we start using our understanding of the situation to go forward. So here is actually where we put the only force that we care about is the force in the x direction, because we know the y and z's are going to come to 0.
Okay.
And so I have to take the component of my total force that's in the x direction. So looking at my geometry here, so I'm back to this slide. I should have been here to begin, so I'm glad you brought me back. Looking at the geometry, you see where the angle phi is the circle with a close to vertical slash through it. Theta is the more like a 0 with a horizontal slash. That's the letter F in the Greek alphabet, is the angle between the mass and the center of the circle and the mass to the edge where my strip is. Theta is the angle, you have to understand what the angles are because we're going to use them. So we use that angle phi to determine the horizontal component of the force. What direction is the force from that little piece? Okay, I forget, it goes different places. If my mass was right here, what direction would the force of gravity be from that mass? The total force. Not just a component, but the total force. What direction is the force of gravity always? Well, on Earth, we define G as the direct force of gravity, but between any two objects, not just the Earth and me.
Well, you were saying, like, where does the gravity go between two objects?
Yes.
Well, they attract each other, but they
always attractive. And so that means the force that this mass would apply to that would have to be in this direction. So that's the direction dF would be from that piece. And of course, as I go around the circle, the dfx is going to be the same for everything. And so I'm going to use this picture to determine how much the dfx is based on the total df. So this is the hypotenuse df. And once again, I have this triangle. Now I say once again, it's not the same triangle. Before I had angle with theta. Now I have phi. But we're looking now for the adjacent side. Adjacent hypotenuse are related with cosine. So that's why we have df in the x direction is df cosine theta. And actually, I put the direction that this little mass would be pulling on the sphere. I should have put the direction that the sphere would be pulling on the little mass, which would be that direction. Right. Okay, so now if we look at this, we have a force in the x direction that is going to be magnitude-wise g times mass 1 times the, what is mass 1 here? It's the mass of this. Times capital M, the mass of my spherical shell, over 2. And then I have sine theta cosine phi over s squared d theta. It's a beautiful equation. It's not super complicated, but it has a really big problem in terms of analyzing. What's the really big problem? Multiple variables. If I change my angle phi, it's also going to change by necessity the angle theta and the distance s. So we've used s here as the distance between our piece of mass on the shell and our mass m that we're going to find force on. So those are interrelated. I have to find some way to combine them so I have just one variable of integration. I can't integrate if I have more than one variable.
So this last equation, sine theta cosine phi,
Yeah.
that one's just a simplified version of those first two. Or integrate.
So the equation, this equation right here, is taking the integral of the x component of this equation here. We actually used this form, and then we took the x components. That's where the cosine phi came from. We had to change the dm to find it in terms of, in this case, it's now in d theta. But it's that equation there. Back to where we are. So now we have to find a way to deal with this theta, phi, and s. And I'm not going to ask you what you think. This is where the tricky part comes. What we're going to use is the law of cosines. We use the law of cosines to relate s. This side here is going to be capital R. The picture doesn't show a capital R in that, but that's the radius of the circle, so I'm going to write it there. S, R, capital R, lowercase r, and both theta in one equation and phi in the other. So we're just going to do the law of cosines twice. So the law of cosines is opposite or side squared. So let's do s squared is equal to the other two sides squared added up minus 2 times the other sides multiplied together cosine of the angle in between those. So in this case, the angle between s and r, or excuse me, between capital R and little r, or the one opposite to s, is theta. So that's one equation that you get from the law of cosines. That's the law of cosines for theta. Now for, go ahead.
You said the last bit again, the cosine of theta is
because theta is opposite to s.
Oh, okay.
So now if I want to do for phi, what side's opposite of phi? Or phi if you prefer. It's got to be r, but it needs to be either capital or lowercase. You got to know. Capital. And so that's going to be capital R squared equals s squared plus lowercase r squared minus 2sr cosine of phi. So we have those two equations by using the law of cosines. And I'm going to solve each one of these for cosine. I'm going to go to the next slide where I've already done the work. So solving the first one for cosine theta, we get r squared plus r squared minus s squared over 2rr. Obviously, capital and lowercase matters. And for cosine phi, s squared plus r squared minus capital R squared over 2s lowercase r. Now, those are good except for one thing. My equation didn't have both of them cosine. It had a sine theta and a d theta. So I'm going to take the cosine theta equation and take the derivative of both sides. What's the derivative of cosine theta? Yes. Minus sine theta d theta. You can't forget that. I didn't say with respect to theta. I just said the derivative. So that's how you know. Oh, yes, Kaylin.
Why are we taking the derivative of it?
Because my equation doesn't have cosine theta. It has sine theta.
Oh, okay.
And it has a d theta. So I wanted sine theta d theta. And look, derivative of cosine theta gave me minus sine, but sine theta d theta. And then if I do the other side, well, capital R is not a variable. And lowercase r is not a variable. Only s, theta, and phi were variables. So that derivative is kind of easy. Because I have constant r squared, constant lowercase r squared, minus s squared. Well, what's the derivative of minus s squared? Minus 2s. And I have to remember I had over 2rr on the bottom. And so I will go ahead and cancel what I can, which is pretty simple. Cancel the minus signs to make it a plus. Cancel the 2's. And I have sine theta d theta is equal to s over, oh, I forgot the ds. Can't forget those d's. S ds over capital R lowercase r. So now I have something to substitute for sine theta d theta. and something to substitute for cosine of phi. So I'm going to substitute the two things I have in black boxes into the equation for df. There's those two equations. So I substituted in, and it comes out to be something pretty simple. I had 1 over s. Let me go back a couple slides just so you can make sure. Yes, that there, by the way, was. I had sine theta cosine phi d theta over s squared. So there's one of the things I'm replacing. There's the other one. And I have over s squared. So the over s squared stays here. Here is cosine of phi. And then sine theta d theta is this. Well, that wasn't very good. That's sine theta d theta. Well, you look at this and you say, I see that I could cancel this s with that s. I have on bottom now a lowercase r times uppercase r. So that's lowercase r squared times capital R on bottom. There was a 2 here, and now I have a 4. Suddenly I'm confused as to why I have a 4 now. Oh, yes, because there was a 2 here as well. So the 2's come together to give me 4. And now I have s squared plus r lowercase r squared minus capital R squared over capital S squared ds. And this is just like the stuff you're doing right now in calculus. That there by itself looks kind of hard to integrate. But if you simply divide the s squared from each term, then it becomes something that's a simple power law integral. So let's do this integral now. I have gm1m over 4r squared r times the integral of this. So let's just do this integral. What's the integral of the stuff in the box? So I'm not writing the GM stuff. What's the integral of the stuff in the box? You have 1 ds. What's the integral of 1 ds? S. And then we have the integral of a constant divided by s squared, or a constant times s raised to the minus 2. So I have the integral of a constant times s raised to the minus 2. The constant stays the same. So I'm going to put plus r squared minus r squared. But what's the integral of s to the minus 2?
B s to the negative 1.
Over minus 1. Which makes it, instead of putting over minus 1, I can just as easily change it to a minus sign out here. So there's my integral. All that's left is determining what my limits are, putting them in, and seeing what I get. So the limits, if you're inside the sphere, the maximum value you can get for s is when it's straight out here, and s is going to be lowercase r plus capital R. So the maximum value for s max is r plus r. The minimum value is going to be when it's over here, capital R minus lowercase r. So our s is ranging from capital R plus lowercase r to capital R minus lowercase r. So those are my limits. Now we already did the integral before. So here I'm showing now putting in the limits for the integral. So here's the upper limit minus the lower limit. Well, capital R plus lowercase r minus capital R minus lowercase r. The capital R minus capital R subtracts out. Lowercase r minus a negative lowercase r gives me 2r. So I have 2r for that first set. So these here combine to give me 2R. Now for the second one, it's a little more complicated looking, but it's really not. Think about this. We had 1 over S, right? So I have 1 over S from the upper limit minus 1 over S from the lower limit is equal to S lower minus S upper over S upper S lower. Right, that's what we're going to have when we put in the limits. And then we say, well, S upper times S lower, that's going to be capital R plus R times capital R minus R. That's got the cross terms add up to 0. And so that's just capital R squared minus lowercase r squared. So that's where this capital R squared minus lowercase r squared came from the common denominator. And then I have to do the subtraction of and make sure you get the order straight, the lower minus the upper. Instead of the upper minus the lower, it's the lower minus the upper, so it's going to be minus 2R here. That minus 2R is basically the same as the plus 2R we just calculated. So what do we get? Well, you have to pay attention to signs here now. I'm erasing everything so we can pay attention to signs. I'm going to change to a different color pen as well. So I have a minus and a minus. So those two together make it a plus. And then this over this is minus 1. Right? Capital R minus lowercase r minus capital R. They're just in opposite positions, so it's minus. And so we have plus a negative. And these two otherwise are going to cancel. So we have one more minus sign to worry about here. 3 minus signs, which makes it a minus. 2R minus 2R is 0. Now that's a really important outcome. If you are inside of a uniform sphere, the gravitational force on you is going to be 0. Which at first seems kind of odd. Think about this. There is a big dome, and you're inside the dome. And you're weightless. That's what this says. It says if you have uniform mass distribution, now you can't just make a dome here on Earth and say, but I should be weightless if I'm inside, because outside of that dome you have a non-uniform distribution of mass. And this is for uniform shells. But if you have uniform shells of mass, it doesn't matter what's outside, you're going to have 0 for your gravitational force inside. So that's a really important outcome. Now we go to what's it like if you're outside of that shell. If you're outside the shell, all of the work we did is exactly the same. All that's changed is the limits. The limits now are going to go from, and you can see the minimum distance would be lowercase r minus capital R, lowercase r being the distance from the center to my point mass, capital R being the radius. So that's the minimum distance. The maximum distance is lowercase r plus capital R. So my limits actually look exactly like they did before, except these two have switched position because of which one's bigger now. So I do the integral again. I put in these limits, and the first term now, the lowercase r's subtract out, and the capital R's are what remain. And then for the second one, of course, it's going to be a minus capital 2R, or 2 capital R, on top again. These here are the same thing now. And so now I only have 2 minuses. 2 minuses makes a plus. So I have 2 capital R plus 2 capital R. That's 4 capital R is what I get for this entire thing. So the 4 capital R, 4 cancels with that 4. Capital R cancels with that 4, or R. And there's my equation for the force. And that equation looks really familiar, right? That's the equation for the force of gravity from a point mass a distance lowercase r away. So what this says is if you're outside of a spherical shell of uniform mass distribution, then the force of gravity between you and that shell is equal to what the force would be if all that mass was just at the center of the sphere. So putting these together, we have two ideas that make it kind of easy to calculate gravitational force. That is, if you have spherically symmetric mass distribution, any mass that is farther away from the center than the point you're interested in is going to supply no net force. Any mass that's of a smaller radius than the position you're interested in is going to supply a gravitational force that's the same as if it was at the center of the circle. So let's put this into practical application because that's where I think it starts to actually make sense. So practical application, okay, that's the description I just gave, is let's pretend, a gross approximation, that the Earth is a uniform sphere with the same density all the way through. Clearly the density is not the same all the way through. I have a graph here showing you how the density varies, and you see that the density is much, much higher for small radii being here, that is in the core, the solid core, and then the liquid core. This is actually the lower mantle and the upper mantle, if you want to break it down. And then the crust. Big differences. But we're going to pretend that the Earth is uniform throughout. If the Earth is uniform throughout, if you are at some distance r from the center of the Earth, what mass is going to matter for the acceleration or the force of gravity? Let's say you are 2,270 kilometers from the center of the Earth at the edge of the molten core. What mass matters to you if you're trying to calculate what's the force of gravity going to be acting on you at that location? And don't get smart with me and say it's not going to matter to you because you're going to be fried. We're ignoring that. What mass is going to matter?
Wouldn't you be technically, if you're referencing from the crust?
I don't even care what the reference point is. I'm just saying, if you're right here, what mass matters to you for calculating the gravitational force? Okay, yours does matter, yes. What else do we have? The what?
5 and 6.
Okay, the masses of 5 and 6, because those are closer to the center than you are. It doesn't matter what the masses of 1, 2, 3, and 4 are. Only 5 and 6 because that's closer. So to calculate the force of gravity acting on you, the force of gravity on you is going to be equal to the density, that's the mass per unit volume, times the volume that is enclosed. So that's going to be the density of the Earth. Oh boy. I'll put density sub E, and then instead of VE, I'll put VENC for enclosed, just to make sure we're clear. That's the mass that's closer to the center of the Earth than you. Then, of course, we have to multiply by the mass of you, that capital G, and over the radius, and I'm going to put radius, I'll just put lowercase r here, squared. Right, that's saying the mass that I'm using for the Earth is just the portion of the Earth that's in regions 5 and 6, as Nathan said. The mass is closer to the center. So how do I calculate the volume enclosed? Well, what's the equation for volume? For a sphere. 4/3 pi r squared. Squared, and I wrote 2. Again, there, I got the 3 written. Aren't you proud? So volume is 4/3 pi r cubed. The density of the Earth, if the Earth had a constant mass, then the density of the Earth would be mass of the Earth divided by 4/3 pi radius of the Earth cubed. Right? Taking the total mass divided by the total volume. And so I'm going to put those in here and say all right, I think I did everything right there. I have the density is total mass of the Earth divided by 4/3 pi times radius of the Earth cubed. And then I have the mass of U, which is my, I have volume enclosed 4/3 pi radius cubed, G over R squared. We can simplify this by canceling some things. So I'll cancel my 4/3 and pi. I'll cancel 2 of those, and I'm left with I forgot to write one of the M's, or maybe I did and it disappeared. So that's the equation for the force of gravity as you go toward the center. You might remember James Pauly asked about this in class the other day. The other day being, I think, Monday. Yeah, it's Monday. Wasn't it? Or was it Wednesday last week? Anyway, he asked about it. Here we have, if the Earth had a uniform mass, the force of gravity would simply increase linearly as you move out from the center of the Earth toward the surface. And when you get to your radius is equal to the radius of the Earth, then the force of gravity is, well, what it is here. That is G mass of U times mass of the Earth. I should put M sub E there for the mass of the Earth. Forgetting things. Over the radius of the Earth squared, if your radius is equal to the radius of the Earth.
So basically, from going from the core up to the surface, it will gradually increase.
It would just increase linearly if we had uniform density.
Okay.
Because we don't have uniform density, it's going to increase more rapidly in the center where you have higher density, and less rapidly further out where you have lower density. Yeah.
Just to clarify the terms, the lowercase r and the RE, lowercase r is 5 to
Is
6,
wherever you are.
and then RE would be 1 to 6.
RE is the radius of the Earth, yes, from 1 to 6. Okay, now, I only did going from the center of the Earth out to the surface. What would it be if we're beyond the surface of the Earth? So like if we move a couple hundred kilometers out, like we had a homework problem, 400 odd kilometers out, what's going to be the force of gravity there? What's the force of gravity there going to be? That's putting it in English. What's the rule if you're outside of the mass? It's as if all of the mass is at the center. If it's a spherically symmetric distribution. And so we just use the equation G mass of U mass of the Earth over radius of the U are from the center of the Earth squared if you go beyond the surface. So then it's going to drop with the 1 over R squared if you go beyond the surface. So if I were to graph the result of this, okay, I didn't make a place to do it, but if I was to graph the result, it would have been something that goes like this. So there's the two equations, a straight line for the going up and then a 1 over r squared decay when you get past the radius of the Earth. I have 8 minutes left, which is really not much time to go into work, but I'm going to do the calculation for the potential energy due to gravity. So we have the force of gravity. If we're just on the surface of the Earth, we say G is constant, force of gravity is mg. Notice I have y hat for the direction there to put it in a scalar. If I want to calculate work, what's the equation for work?
Force and distance.
Okay. There's an important thing to note there, though. It's force dot dx. Right? It's the parallel parts of the vectors. Well, we're in calculus class. We can deal with a force that's continually changing. But what we're going to have to do is say dw is equal to force dot dx. And then we're going to integrate. Hey. So let's start with the easy. What's the work done? You know, I did nothing wrong. That little spike wasn't my fault. I did a rectangle. It is. Hopefully something you can reset by turning something on and off. So if I apply this to this equation, remember in class, I said the area under the curve is the work, and then we looked at the curve and we worked from there. Well, here we can do it directly. Force is minus kx. So that's going to give me work is equal to the integral of minus kx vector. I need to change colors because it's the same color as my graph. Well, that's not hard to do for the integral. First of all, let's look at the dot product. Those are vectors. What is x dot dx? The x direction dotted with a change in x. They should be in the same direction, so it's just x dx. Right? Because the first thing you have to do is resolve the dot product so you get scalars to do the integral. So we do the integral of minus kx dot dx is going to be just, since x vector dot dx vector is just x dx, then the minus k has to stay integral x dx. Well, what's the integral of x dx? It's what?
Yeah, it's square root.
Okay. I thought I heard square root. That's why.
You must don't do that to me.
Okay, so the work is minus kx squared over 2. Now, I want to go to potential energy. Potential energy is defined that the negative, or the change of potential energy is minus the work. So if that's the work done by the spring, then that's equal to minus change in potential energy. And of course, this would be going from x1 to x2. So I would have, since there's a minus there and a minus there, I'm going to get rid of the minuses. And I'll have kx2 squared over 2 minus kx1 squared over 2 is potential energy 2 minus potential energy 1. Any genius can say, hey, it looks like kx squared over 2 is the potential energy. Now, anyone that thinks about it a little harder could say, not so fast. Potential energy could be kx squared over 2 plus 5. That would also work, right? Because potential energy 2 minus potential energy 1. the minus 5s would cancel. Or they would subtract out, excuse me. But by convention, we say that would be ridiculous. We say potential energy, we're just going to use kx squared over 2. That's how we get it. Force of gravity is even easier. Force of gravity is minus mgy. So if I have something that moves from here to here, x goes from, let's say, 0 to 5, and y goes from 0 to 3. If I want to calculate the work done by gravity, which of those am I caring about? Just the y component. So when I do, if I want to be all technical-like, I could put the work from gravity is integral force of gravity dot dr vector, where dr is not saying x or y direction, it's saying whatever direction I move. But the only part that's going to be parallel to the force of gravity is the vertical. And so we end up with minus mg y dy. What's the integral, or excuse me, minus mg dy? Well, what's the integral of minus mg dy? Mg is minus mgy, which means the change of potential energy is negative that plus mgy. Hence you get potential energy is mgy. Easy. This one here is the last one. That's the one that is the least obvious. And so that's a minus sign there. Yeah. So I put it that way with the r hat. And then if I want to find the work, the r hat and dr are the same direction, so it disappeared again. And I have the integral of dr over r squared. Well, what's the integral of dr over r squared? We've done this integral already once today. It's negative 1 over r. And so this gives us then negative and negative makes a positive. And you're all, yay, the work is positive. Now remember, we're going from R1 to R2. So the work is G M1 M2 times 1 over R2 minus 1 over R1. But then if we want potential energy, the potential energy change is minus this. And so I have U is the same as potential energy. So here's the minus sign that comes from there. And then the rest is the work, because it's minus the work. And so that's potential energy 2 minus potential energy 1. And you see immediately, well, then that means potential energy 2 is minus GM1M2 over R square over R2. Or potential energy is minus GM1M2 over R. I've used up my time. We've done a lot of work. Kaylin.
Sorry, where did the negative sign come from? I thought we canceled it out in the integration.
Okay, so there was no negative sign here. But this negative sign here, the change potential energy defined as minus the work conservative is where that came from. Okay, I will see you at 2:15 defy gravity, except for Micah.
I have a question though.
I'm sure.
So for that to make a size, we have to always it's just